Welcome. In this introduction, we're going to cover the important questions: what is information visualization and why use it? So there are lots of things out there that we call visualization. For instance, in journalism, it's very common to have interactive charts that journalists use to present some information. Or in scientific communication, we have many images and visualizations in papers to explain scientific phenomena. Or in many companies, we have dashboards that help people make decisions or monitor certain situations. And we also have things like libraries or tools that help people develop data visualizations. And we also have domain-specific visualization interfaces that solve very specific problems. And we also have a lot of art and design. So visualization can also be used to express things in artistic ways and to provoke emotions, for instance. But all of these things have one thing in common. What do they have in common? Well, they literally deal with the problem of turning data into graphical representations. However, this is not the full picture. Interestingly, information visualization or data visualization, as is also commonly described, is not just about taking data and finding a visual representation for the data set. So let me try to give you a more complete picture of what is going on in visualization. First of all, the first thing to understand is that data comes from some kind of data generation process that captures aspect of reality we are interested in. So this is what we call raw data, and it's always a coarse or limited representation of reality. Then we have what I like to call derived data. So we transform the data in order to extract the information that eventually we want to visualize. So this means that we have a lot of leverage in transforming the data and extract out of it the information that we need. Then we have what we call visual mapping, or sometimes also called visual encoding. That is the actual step of taking this information and mapping it to visual representations. But that's not the end of it. What else do we have? Well, typically visualizations exist in an environment, often within user interfaces when we are building tools, or all sorts of documents. It can be static documents, it can be interactive documents, it can be presentations, it can be a lot of different things. But what is really important is that visualizations actually exist within a larger context. And that's what I like to call arrangement. And finally, we have maybe the most crucial step. Well, there's no visualization without someone absorbing that information. So we have the actual readers or users, and the last step is perception and cognition. There's no visualization without someone perceiving and thinking about the information that is presented in a visualization. And one thing I really like to stress is that despite all these steps in between, the reason why we use visualization eventually is because we want to understand the reality that is captured by the data. Now, before moving on, there's actually sometimes another step here. What is it? Well, it's interaction or interactivity. Visualization doesn't have to be static. In many situations, it's not static. With the advent of computers, it is possible to create interactive visualizations that can be manipulated. So the other step here is that for interactive visualizations, it is possible to change one or more of these parameters interactively. Okay, but why visualize data? What is the actual goal? Why do we want to visualize data in the first place? Well, there are many reasons. Let me try to cover a few ones. So the first one is related to what I was saying before, to understand the world through or with data. Ultimately, our interest is not in the data itself, but in the idea that data can capture relevant aspects of the reality we are interested in, right? And effectively, in the end, what do we generate with data visualization? We generate new ideas, decisions, new knowledge, hypotheses, questions, and so on. So this is what really, really matters, okay? And in relation to that, another thing that really matters is whether the knowledge that is being generated is reliable and useful. So that's step one. Second goal is also to communicate information effectively to others. So it's possible that we already know what is that information, but we want to communicate that information to other people in an effective way. What we see here in this image is Hans Rosling, a very, very famous scientist who unfortunately passed away a few years ago, who gave these amazing visual data presentations to explain how the world evolved during the last few decades. And then he wrote this really interesting book called Factfulness that covers some of his principles about presenting the world through data. But that's not all. What else? Well, data visualization is also used for many, many other purposes. For instance, to inspire, to reflect, to entertain, and who knows what else. It's actually open. It can be used for any purpose that we think it's appropriate for, right? And that's what is captured by a really interesting book by Alberto Cairo called The Art of Insight, where he's interviewing and describing the artistic process or the design process of many visualization designers. And in this book, he's arguing exactly the same thing, that visualization is a lot of different things. Okay. Now, in this book, in this course, we will focus almost exclusively on the data analysis and presentation part, but I think it's really important for you to know that visualization is much larger than that. So now you may ask, but why use visualization exactly, specifically to do these things? So for instance, why use visualization to communicate information or to understand things about the world? When does it work? When is it a good idea to use visualization for these things? And what else is possible to use? Well, the main answer to this question is because it can, when designed correctly, turn complex information into things that are very easy to see. When a visualization works well, it becomes almost obvious what is the information to extract and what this information means. So let me give you an example. I really like to give this example to express this idea in a more tangible way. What you see in this table is information about a number of airlines. So what you see here, in every row, you have one airline, and in every column, you have 1 hour of the day, time hour. And the numbers that you see inside in the tables is the typical amount of delays, or the average amount of delay that airline has at that time of the day. Now, I want you to try to answer the questions that I pose by looking at this table. So try to do it, and if necessary, stop the video for a moment to see if you can answer that question, and also how hard answering that question is. So be ready to do that. Question 1. At what time of the day are delays most common? Try to answer that question. So if I had to do that, I'll try to eyeball this table, and I see that there are larger numbers somewhere around here, but it's hard to be confident about that, right? Let's try with the second question. Which airlines have the highest amount of delays? So now I'm kind of like scanning row by row, trying to see some numbers, but I'm not really sure. I can't tell. And next question. Which airlines have the largest increase in delays during the day? So now I have to look at increase. So now it's not only I have to focus on each row at a time, but also how steep is the increase at any given time. That's really, really hard. Okay, so now let's try to do exactly the same thing, but with a graphical representation. So I will go through the same questions and now try to answer the same questions looking at the graph that I'm going to present. Once again, I suggest you to stop, pause the video for a moment and see if you can answer and how it feels like compared to doing the same task with the table. So question 1, at what time of the day are delays most common? Well, now it seems pretty obvious, right? I can see that between 2:30 and 9, it's definitely the peak, right? Most airlines, except that these two airlines here have peaks shifted to the right, so later in the day. Interesting. Question 2, which airlines have the highest amount of delays? Well, now this is super obvious, right? I don't even need to think about it. These two, right? These two up here, they are the tallest. These have the highest amount of delays overall. Very easy. Next one, which airlines have the largest increase in delays during the day? Well, that's also not that hard. Look at this one, the purple-pink one. It goes up really, really steeply here. And the green one, again, it goes up really, really steep. So here it's similar to the previous ones, and then it goes up very, very quickly. So that's also very easy to answer. Okay, so now I want you to imagine communicating this information not with a table, not with a graph, but with natural language. So let me read this text to you. The average delay increases steadily throughout the day, starting from 6 a.m. until around 9 p.m. Much higher delays take place between 3 p.m. and 9 p.m. And among the airlines we considered, EV and WN experience much steeper increases. EV experiences in general much higher delays than all the other airlines regardless of the time of the day, and so on. So imagine if I had to describe all this information just using natural language. It would be very hard to build a mental picture of what is going on. Whereas when I show you a graph like this one, it's immediate. It's pretty obvious, right? So this is what I mean by the power of visualization is turning complex information into something that is easy to see, almost obvious. When visualization is used properly, often the result is what you have just experienced here. So, in general, there are three main modes or modalities to communicate and to absorb information. The one that we have covered in the table, I like to call it symbolic. It means that we are absorbing information through some symbols, in this case, through numbers and labels. The last one that we saw is verbal. We are using natural language to communicate information. And the last one is graphical. So data visualization is in large part rests on the power of graphical information. Now, it's really important to realize that graphical information is not the only thing that constitutes a visualization. It's always a mix of these elements, but the power of visualization and the reason why we use it comes from the things that we can do effectively and efficiently with graphical representations. Okay, now I want to give you a sense of the power of visual representation through another example that I really, really like. And to do that, we will have to play two games for a moment. So let's play what is called the game of 15. So how does the game work? The rules. So the pieces for the game are the 9 digits between 1 and 9. Each player takes a digit in turn. Once a digit is taken, it cannot be used by the other player. And the first player to get 3 digits that sum to 15 wins. Okay? So if this is not clear, pause the video for a moment and read the rules again. Okay? Now, let's look at a sample play. So player A takes 8. Player B takes 2. Player A takes 4. And player B takes 3. And player A takes 5. This is the classic tic-tac-toe. So what are the rules? Players alternately place a knot, the symbol O, or a cross, the symbol X, in one of 9 spaces arranged in the grid. Once a space has been taken, it cannot be changed by either players. The first player to get 3 symbols in a straight line wins. I hope you played tic-tac-toe before. It's pretty straightforward. Well, because the two games are exactly the same problem. If you arrange these numbers in the grid, you will see that every row, every column, and every diagonal sums up to 15. So when this game is presented in one way with a given representation, it tends to be really, really hard. But when it's presented in a different representation, with a different representation, it becomes way, way easier. And in particular, the second representation is a graphical or spatial representation that makes playing and understanding the game way, way easier. So this, if you're curious, is the situation of the play when you have to play the next step, right? So if you put the symbol there, you know exactly what is happening. So this problem is what scientist Herbert Simon called problem isomorph. What is a problem isomorph? Is the idea that that a problem can be represented in many, many different ways. So they are isomorphic. They have exactly the same rules and exactly the same constraints. But when something is represented in a different way, all in a sudden it becomes much, much easier. Isn't that fantastic? It means that in principle, for many, many problems that we have out there, if we find the right representation for the problem, it might become way, way easier to solve it. So this is expressed in a fantastic book that is called The Sciences of the Artificial, and also from other sources. So this is what Herbert Simon calls problem isomorph, and it's a perfect example or perfect explanation for why certain visualizations work so well. So the second thing that I want to cover here is that visualization is also ideal when we have open-ended questions that we want to answer with data. Let me describe that in more details. So to do that, I'm going to use a data set that I will keep reusing very often in this course. This is the New York City vehicle collisions data set. In this data set, every single row represents one collision in New York City. And now for every collision, we have a large number of variables. In particular, we have the borough where the collision happened, the zip code, the crash date, the crash time, the vehicle type, the contributing factor, the number of people injured, number of people killed, and so on. Many, many attributes. So now let's look at what kind of questions we might want to ask and answer to a data set like that in order to understand vehicle collisions in New York City. So some closed-ended questions. Which borough has the highest number of collisions? Are there more collisions during rainy days? Has the number of collisions increased compared to last year? Or is there a correlation between temperature and number of collisions? So what all these questions have in common is that they can be answered with a single datum or number, right? So which borough has the highest number of collisions? One borough. I don't know exactly which one right now, but it's one borough. Are there more collisions during rainy days? It's either yes or no. Has the number of collisions increased compared to last year? Again, it's either yes or no. And is there a correlation between temperature and number of collisions? Well, we can answer with the correlation coefficient here, a common statistic, and it's just one number. But what happens if we have open-ended questions? And open-ended questions are really important. Let me give you a few examples. How do the collisions distribute across New York City? How does the number of collisions vary in relation to precipitation amount? How has the number of collisions changed over time? And how does the number of collisions vary in relation to temperature? So I designed these questions in a way that they are almost like match really, really well with the other questions, but instead of being closed-ended, they are open-ended, right? And what all of these questions have in common is that you can answer them with just a simple answer. It's more qualitative. So let me give you a couple of examples. How do the collisions distribute across New York City? Well, when I show you a visualization like this one, you can start understanding the answer to this question, but the answer to this question is not one single number, right? It's qualitative. It's not necessarily quantitative. How about this one? How has the number of collisions changed over time? Again, when you look at this graph, you can start describing what happened, but it tends to be more qualitative than quantitative. It tends to be more nuanced rather than a yes or no answer or a single number of statistics. Isn't that interesting? So visualization shines when the kind of questions that you have are these open-ended kind of questions. So this also gives me the opportunity to talk about statistics. So when we deal with data, we often use statistics to reason about data, right? In fact, statistics is the science, right, or the discipline that helps people deal with data and extract information out of data. So statistics are great and very useful in many, many situations, but they also have a number of problems that are addressed by visualization. So here is what is called the Anscombe's quartet. Anscombe was a statistician who came up with this brilliant idea of creating these four synthetic data sets that look really, really, really different, right? But they have exactly the same statistics. So if you calculate the average of X or the average of Y, you'll find that they have exactly the same number. If you compute the correlation coefficient, you get the same number. If you create a regression line, you get the same regression line. If you compute the variance or the standard deviation, once again, same numbers. Isn't that brilliant? So if we used only statistical aggregations, we wouldn't be able to distinguish between these four very different data sets. So this gives you a sense of the fact that visualization can help unpack the black boxes that you have behind statistics and computational procedures. So after seeing all these examples, you may think, wow, visualization is fantastic and I should use it for every single problem I have out there because it always works and it always makes information easier to absorb, right? Well, unfortunately, the answer is no, that's not the case. And let me explain to you why. Well, first of all, not all data problems require human involvement, and data visualization inherently requires human involvement. So there are many things out there that should be, and we want them to be automated. So this is the realm of data science, machine learning, and many other areas of computer science. And when something needs to be automated through a lot of data crunching, that's fine. There's no human involvement necessary. Just to give you a few examples, if I want to create an intrusion or fraud detection system or recommendation systems or something that powers the search engines, all these things crunch a lot of numbers, a lot of data, but doesn't necessarily require a lot of human involvement. But there is more. There are actually bigger problems with data visualization. It's not just that for certain problems it's not adequate. The bigger problem that is more relevant for us is that if you design data visualizations in the wrong way, if you don't design them properly, you can have problems. You can generate problems. So it's no longer effective. So visualization can be confusing. Let me give you an example. This is an example that I like to use. It comes from, it's a climate change graph that it's meant to communicate information about how much risk there is at different levels of temperature. And I always struggle to understand what is the meaning of this graph. Even though I have seen it before, every time I see it, I have to relearn exactly how to read it. And I suspect that this comes from two problems with this graph. The first problem is that here on the vertical axis, you have temperature, right? And color here represents risk. But my mind wants to read color as temperature, so somehow these two ideas clash and I'm confused, right? And the second is the fact that this chart looks a lot like a bar chart, but it's not a bar chart, so I'm always confused and I don't know exactly what these bars represent. So visualization, if not designed properly, can be confusing. But it can also be biased or misleading. Here I have a second example, again coming from climate. This is an example that I took from my colleague Michael Correll. This is exactly the same information, temperature over time, average global temperature over time. And the only thing that changes from between the graph on the left and the one on the right is whether the vertical axis is truncated or not. On the left, the axis starts from 0, and on the right, the axis starts from a much higher value, right? And what you can see here is that if you choose to start from 0, the line looks completely flat, and you can conclude a completely different kind of phenomenon. You can come up with completely different conclusions. Whereas if you look at this one that is truncated, you think, wow, it's going up and really quickly. right? So this means that choices that you make when you decide to visualize data can make a really, really big impact of what messages are conveyed, right? So visualizing data one way or another is not neutral. And here is another example. So if I have vehicle collisions in New York City, and I ask, what are the most dangerous areas of New York City? And I show you this map where every region represents a zip code, and the color represents the number of collisions. And once again, I ask you, what are the most dangerous area of New York City? You would probably look at the darkest spot on the map and think, this is the place. This is where it's really dangerous, right? But wait a minute. It's more complicated than that, because this is the number of collisions, but the number of collisions is also related to how many cars are in any given region at any given time. So it's correlated to that. So if there are more cars, there are more collisions, but it doesn't necessarily mean that it's more dangerous. So this is the problem with translating the idea of most dangerous with number of collisions. So if I show you, instead of number of collisions in the same type of map, the average number of people injured in a collision, you have a completely different map, or a very different map, right? And you would point to other regions to say, what are the most dangerous areas of New York City? So this means, once again, that different choices that you always have to make choices, and different choices lead to different interpretations, which in turn means that the way a visualization is built can skew interpretations in one direction or another. Finally, visualizations can also be terribly ineffective or inefficient. So it doesn't mean, if you visualize data, it doesn't mean that extracting information from a visualization is always effective and efficient. And here is an example that shows you that. So this is a chart that represents the causes of untimely death, right? And every single rectangle here, it's a sort of cuboid, right? But every rectangle represents one specific kind of disease, right? Or cause, not necessarily disease, cause of untimely death, right? But I don't want to focus on that. The thing I want to focus on, if you look at the legend at the bottom here, we have the annual change, percent change between 2005 and 2010. Right? So if you look at the colors, you should be able to identify how much change there is between 2005 and 2010. Right? It seems pretty straightforward and easy. However, if you look at the legend, you will notice that there are positive changes and negative changes. Right? So you see there's 1%, 2%, 3%, and minus 1%, minus 2%, minus 3%. Now the problem is that if I now ask you to distinguish between or identify causes that had an increase or a decrease, it's really, really hard, because it's hard to distinguish between positive changes and negative changes. And as you can imagine, that's really, really important. So the choice of specific visual encoding, the colors that are used here to represent change, are not appropriate. They're very inefficient and ineffective. Okay, so unfortunately, as we have seen, it's not sufficient to just visualize data to have some positive results or positive outcomes. You have to learn how to design effective visualizations. And that's why you are taking this course. And that's what I'm hoping to communicate to you during the course of these lessons. Okay? So the key questions that we have to answer now is, how do you learn to develop effective visualizations? Well, I like to think about as acquiring two main skills. And to explain that, I have to show you a little diagram. This is inspired by work by Professor Tamara Manstner. She has a very similar diagram in her book. So if we have a data analysis or communication problem and you are a visualization designer, the thing that you have to do basically is to explore the design space of solutions. But now the design space of solutions, most of the time, I would say virtually every time, is really, really large. And that's one of the biggest problems with visualization. The design, the space of solutions is very, very large. So how do you go about finding appropriate solutions within this design space? Let me remind you, if you remember the diagram that I showed you at the beginning, that visualization is not just about finding the right visual representation, but it's also about, for instance, finding the right data transformations, okay? So it's more complicated than just visual representation. So what do you do? Well, first you consider the solutions that you can come up with, right? It's very likely that you don't have a full knowledge or access to all the possible solutions. So you search within this space, and there are some solutions that you consider as possible or plausible or applicable, right? This is the considered solutions. And within these ones, you pick the effective solution or solutions to use for your problem. Okay, so when you do that, you have to develop two main skills. The first skill is generative skill. So the generative skill means that you can generate as many appropriate solutions as possible, right? So as I said, the design space of solutions is very, very, very large, and you have to be able to explore or ideate or conceive as many as possible. So now the second skill that you have to develop is evaluative skills. So out of those ones that you've been able to think about, you will have to decide which ones are effective. So what I really like to tell students is that they have to develop these two main skills, being able to generate a lot of solutions and then being able to evaluate them. How do we do that? Well, typically for generative skills, you have to acquire a large vocabulary of visual solutions. So this means going through a lot of examples, right? And then learn systematic methods to generate alternatives, which is something that we're going to cover in this course. You will see that we're going to use models that teach you how to think systematically about how you can generate many different solutions for the same problem. And for the evaluative skills, we will use principles of human perception. That's the most powerful thing that you can learn, right? If you know a little bit better about how visual perception works and how this knowledge, these notions can be applied to visualization design, you will have very powerful skills to predict what works and what doesn't work in visualization. And then related to that, also a series of design guidelines and heuristics. There are simple rule of thumbs that you can use to make decisions in visualization design. So I want to emphasize an idea that I'm going to cover again later on in the course. So you start from a problem formulation or goals, right? And then you have to develop questions, then data transformations that produce information, and then visual encodings that generate representations. Now, the really important aspect here is that you have to learn to do a number of things. First, generate the right questions for the problem. So if you don't generate the right questions for the problem, it doesn't matter how good the rest is because you're answering the wrong questions. Second, generate the right information. If you're not using the right procedures to generate the right type of information that is necessary to solve the problem, well, the visual representation doesn't matter because you're not visualizing the right information. And finally, how to produce the right representation. So we will come back to this notion over and over again. But visualization design is not only about coming up with the right representation, but it's also about identifying the right questions and the right information. So often when somebody calls me to get help and they want a visualization expert, they come to me and they ask, what's the best way to visualize this data set? And this is exactly the wrong question, because you can't decide what is the best visualization for a data set if you don't have a specification of what is the goal, what are the questions, and what you want to eventually communicate. So a better question is, what's the best way to answer this question or these questions with visualization? So when I have new collaborators and they ask me what is the best way to visualize some data that they have, I get back to them and I ask, what are the questions that you have? Can you give me a list of questions? That's a super powerful method to design effective visualizations. Or what's the best way to communicate this idea with visualization? What do you want to communicate? Is the problem is communicating something? The question is, what do you exactly want to communicate? So once again, there's no such thing as the best visualization for a data set. You can only decide if you have a specification of what are the questions, or at least what is the communicative intent.